So hi everyone, my name is Catherine Ordun. I'm a senior data scientist at Booz Allen Hamilton. For those of you who do not know what Booz Allen Hamilton is, what it is not is a law firm. Because people are often like, oh, you must have 3 partners. So it's not a law firm. We're actually a large consulting firm based out in Tyson's Corner, which is in McLean, Virginia. It's only about 20 minutes from DC. We provide a lot of consulting services all across the world for mainly governments. So we even have some international presence out in Saudi Arabia, for example. We do cybersecurity consulting for the kingdom. We do a lot, probably 97% of our work is in federal government for the country. And the types of work that I personally lead as both a senior data scientist as well as a senior manager within Booz Allen are developing machine learning prototypes for the defense sector and also the health sector. So that gives me a really great opportunity to both code a great deal, which is a great passion of mine, and then also to work with a lot of very smart people who are coming out of undergraduate and graduate programs hailing from multiple backgrounds. A little bit about me. I actually have a background in public health and biology, and I started at the CDC as an injury epidemiologist many moons ago. And from there, I really wanted to work in public sector. That was my natural desire, so my entire life, I've been working for the government. So after CDC, I worked in some biodefense projects over at DARPA. After DARPA, I worked in the intelligence community. And then naturally, I started working at Booz Allen. So I've been at the firm for about 7 years. And what I'm going to talk about today is using Jupyter Notebooks as a tool for being more transparent about how we build machine learning models for the government. And I'm going to walk you through a case study that deals with disease modeling for a U.S. Defense Health Agency. Now, in the abstract for this session is probably very technical, and so I want to let you know that since this is the business summit, you may not realize everything in Concourse A is a business summit, that my goal is to not necessarily show you how to build a recurrent neural network for disease modeling, but I want to show you the so what, the reasons for why showing this code in a notebook is important and valuable in terms of being transparent. The talk is going to be in 2 different parts. So the first part, we're going to go through a presentation. I think that's going to appeal to the business leadership in the room, again, emphasizing the story of transparency and so what. And then the other half, I'm going to walk you through a notebook. It's going to go through one particular example, and I'm going to show you what I have embedded as transparency value add. That's my consulting speak, meaning it's the so what. Who cares about why this code is even helpful at all? Let's go ahead and begin. There's my handy clicker. All right, so in terms of the US government, the Department of Defense really leads the way when it comes to machine learning. Lately, they've done a lot of work called Algorithmic Warfare, Project Maven, that deals a lot with computer vision on images and full motion video. But we'll see just through some of these articles that really ever since the beginning of the 2000s, advanced analytics using machine learning, statistical models of machine learning, have really coalesced at the DoD, NASA, as well as the intelligence community. Now, although the DoD really leads the way when it comes to innovation with machine learning, not every single government agency is on board. So there are even offices within the DoD where doing data science is new. Doing machine learning is also very brand new. So the organization as a whole is really starting to dip their toe in the water, and anything that we can do to help them better understand, both from an area of transparency as well as client education, is incredibly helpful. Now, other parts of the government aren't really sold on machine learning and AI. This particular article cites a survey of 100 different C-level executives in IT within the government. And really only a quarter of them think that machine learning and AI is important to their agency's mission. I think 25% is actually pretty good. And so, why is this happening? Well, there are multiple factors related to the government writ large about why these leaders are not adapting machine learning at a rapid pace. Undoubtedly, I would say that one of them is that machine learning is hard. Machine learning suffers from a paradox, I'd like to say, where our previous speaker had noted it's very easy to run machine learning code. You get 3 lines of code, you're doing machine learning. It's another kind of beast altogether to be able to explain why you chose that model, how the algorithm works, how you can interpret the model, and then do it again 100 different times. And so the whole idea of being able to be a little bit more transparent when we build these models for the government is absolutely paramount. These really speak to several questions I myself have had to answer in my 15 years in government. From the Treasury to the intelligence community to the FDA, the VA, the Army, multiple government leaders, scientists have asked me these questions. And a lot of it comes from probably things that you might be experiencing in your industry, which is there's a big talent gap. We've got a lot of very, very smart people who are graduating right now, and I really believe that in the next decade we'll kind of be able to bridge this gap. But as we can all see in government and industry, it's much more attractive salary-wise to go to industry than it is to government. So we don't really have the ability to marry up this talent bridge. Hence, one of my questions basically points to, what are we going to do when all the consultants leave? This points to a much larger theme that's been permeating within the machine learning world right now, which is all about replicability and transparency. This is a Twitter thread from about a week ago with some luminaries in AI, and they are lamenting about how being able to duplicate and reproduce academic research is hard. So they look for the code, and it's just hard to replicate these methods, especially when it comes to something as complex as deep learning. But our thesis is that while it's also important in academic research, it is just as important to a government, particularly when that organization is just getting started. So the value proposition for using a Jupyter Notebook is very, very high when it comes to transparently documenting how we build these models. Now, before I ever knew what a Jupyter Notebook was, I think when it was called IPython Notebook, about 2 years ago, I was doing the uncool thing, and I was coding everything in my IDE of choice, which is Spider, which is not as cool as PyCharm. And I was just writing functions and writing a main.py and running it. And I would explain to my fellow data scientists, hey, this little bit is how I built the model, eyes would glaze over. So it's hard to explain how your code works to your fellow data scientist. How are you possibly going to explain it to a government project manager or to a scientist who wants to be able to run your code? So the very base minimal specs, just the better readability of your code in a Jupyter Notebook makes machine learning very helpful. Not only that, but there are many opportunities for explanation in a Jupyter Notebook. What I'm going to show you in my notebook is it comes down to using a lot of pictures and diagrams. So putting out diagrams for how you are shaping your data, a diagram for your model's architecture, obviously being able to visualize some of these methods like your loss plots, as well as having little brackets where you can talk about the research, your references, etc. So the basis of being able to read your code and to explain it and hand it over to someone and walk them through is a fundamental value proposition of the Jupyter Notebook. So we're going to go ahead and dive into our use case. So for the prototype that we built for this Defense Health Agency, they wanted to better forecast future cases of pertussis, which is whooping cough. And we've been working on not the whooping cough problem, but the overall problem since December. Now, what we wanted to do was investigate a particular type of machine learning model, or what you might popularly hear as a neural network, called a recurrent neural network, or an RNN. Now, RNNs are very good at being able to pick up patterns of historic sequences of chronological data and be able to predict the next sequence in the future of that chronological data. So they naturally lend themselves well to problems like natural language processing. We're looking at what is the next word in the sentence because all the other words before it have context and meaning. Also for this problem, very good fit for potentially investigating its use for time series forecasting. Because all the patterns in time have a historic pattern, we want to use it for forecasting in the future. Now, recurrent neural networks have a specific type of model that we're very interested in using called an LSTM, or a long short-term memory unit RNN. You have to learn a lot of acronyms in this space. LSTMs are not new. They're not something that was just invented a day ago. They were developed in the 90s from Hawkrider. A lot of these methods are based on sound statistical methods using a lot of calculus. But because we have high GPU compute today, we've got a lot of data, there's a lot of research, it makes it a fruitful time to do deep learning. Now the plot on the left is by an author and group called Wei et al. And what they did is they predicted stock market prices on multiple stock indices using multiple types of LSTMs. So doing a univariate forecast for only predicting stock price. We wanted to know, do you think that we could take an LSTM and apply it for multivariate time series forecasting? Meaning that in the public health sphere, there are many environmental factors that influence the outcome of disease. That could be climate, environmental, demographics, other disease factors, and being able to do time series forecasting in and of itself is incredibly challenging and hard. And I'll say that we have not solved this challenge. It's very hard. If we could all solve time series, I think we'd all be millionaires because we could predict the stocks for tomorrow and the next week. So our goal was to build a multivariate time series forecasting model using an LSTM. Now, in the notebook that I'm going to show you some of the code of how we built this model. I'm going to show you one example. That's not anything to write home about. That's pretty ordinary. And I think in a lot of the excellent tutorials this week, you've seen how people build models. However, when you pull them all together and we bridge together the functionality of how do we process and transform the data? How did we evaluate the model? How can we plot the predictions? How can we visualize the training loss? How can we look at the weights or compute the gradients? Together, all of these different components make it a lot more transparent about how we are building these models for the government. So let me go ahead and switch over here. And I'm hoping that we'll have some time for questions here as well at the end. All right, now the first thing that I want to orient you to is this. I really like NB extensions, which is a Jupyter package, or I don't know if it's a package, but it's a plugin. And that's why I've got a table of contents. When you're building a lot of models, it's very hard to keep track of what you're doing if you don't have a table of contents. So here's your first step towards readability. What I'm going to do, because some of this code is technical, I created a very simple example. At the end of this notebook, I will show you a final notebook with 7 similar examples. But because it makes no sense to go through 7 different examples, this one is very representative of what we've done. What I want you to see in this notebook is get a sense of why this code that I'm showing you is helpful when being transparent about building a model. Now, another part of this is that this is not just a trend. This is not something I just think is cool and I just want for everyone at Booz Allen to use. As a senior data scientist and also a senior associate, I write and respond to a lot of government proposals, meaning that I am writing a technical approach that tells the government, here's how we would execute this work in machine learning and deep learning if you gave us that opportunity. And as a part of writing into that timetable and schedule of deliverables, I write in to have a Jupyter Notebook as a part of the deliverable at every single sprint review. So this is something that I'm very committed to, that I really think is gaining great adoption across Booz Allen, and especially for our clients that are doing a lot of this work. All right, let me make sure that we can see this. Let me just blow this up a little bit. All right, so we're going to talk about 2 ways of doing time series modeling. Now, there are a lot of great references out there for time series. So while this presentation is not about time series, I've embedded a couple of references. At the end of this session, I have this on my GitHub account, so you can have this notebook. And I'll also show you how to have it on Google Collaboratory, which I've put up as well. So you'll get to keep all of this. Don't feel like you have to scribble down notes furiously. The first way to do time series, we can model the stochastic process. So that means decomposing the seasonality, the noise, the trend, and implementing a model like ARIMA. We're going to do that. Another way is to use a supervised machine learning approach, which means we've got all this historic data, and we've got a target. What's our target? Pertussis cases. That's the thing that we want to predict. So let's use this example to explore both of these different methods. We're going to use data that is from the National Oceanic Atmospheric Administration acronyms, or NOAA, for our climate data. And we're also going to use data from our partner at Booz Allen, Los Alamos National Labs, called EpiArchive. You can go online to epiarchive.net, I think. And we access the API that they gave us, but they have time series disease case counts for multiple diseases all around the world. 544 time steps. Every single time step is 1 week. Around June 2007 to September 2017, roughly a 10-year period. Our goal, forecast weekly pertussis cases. All right, so here we go to what I'd like to tee everything up for. This is a diagram that I use with my teams to explain how we build some of these machine learning models, especially because I'm in the business of building prototypes. And what this is telling me is that we have a problem definition, which is the first most important thing. What is foolish to do is, from a model building transparency perspective, is just, hey, let's just build an LSTM. Let's just do it. That's foolish. What we really need to do is define the problem carefully and methodically. After that, we get some data. We build some data models. Now we're ready to do cool stuff. We build the initial models, we evaluate them, we interpret them, we inspect them. The whole process, by the way, as some of our speakers made a point in our keynote, we are not data scientists. We don't just do this by ourselves. We are not unicorns. We work with data engineers, with SMEs, with scientists, and with managers, the entire process. Again, another reason why a Jupyter Notebook makes that transparent. Finally, ready for beta deployment. Now, what these feedback loops entail, and I'll tell you why this is even important to this notebook, is that sometimes things can go real haywire and they can go wrong. The first feedback loop that I've experienced is I've interpreted the model incorrectly, or I just haven't interpreted it correctly at all. Another problem for mistakes, maybe the data models were incorrect. We don't have the right data, the data is biased, we don't have enough data, we really mucked up how we transformed it. Go back to data models. Many cases, sometimes the problem defined was not careful. It's the wrong use case. We shouldn't be using machine learning. Maybe there's something else that's more fundamental. Go all the way to the back and do problem definition. Now, when I showed you my slide of like my wonky code that I showed you in Sublime, which is not fair, and how I did everything in Spider, you can't really do this and visualize these different steps very nicely. At least in a Jupyter Notebook, this provides me a roadmap, a voyage journey for how I can chronicle each one of these steps. All right, so we're going to load in the data here. Again, we've got 10 years of weekly data. And let's just kind of take a look at what this data looks like. So here's our pertussis data at the top. We see a little bit of a spike around here, but it's kind of random. We've got our influenza data with a lot of data points towards the last years. We've got our precipitation from NOAA, and then we've got, salmonella, precipitation, high and low temperature, which of course are very, very seasonal. Now here's what we first need to do. Here's my consulting speak. Transparency value add. This is the so what. All right, so with our baseline model, what we try to do is start with something that we already know, start small so that we can leapfrog into something larger. In my personal humble opinion, I do think it's foolish to immediately start on a novel problem dealing with neural networks or machine learning. I think that for a new organization, such as a government organization where they've never done machine learning, it's important to use a tried and true process, or at least a process that the organization has been using already way before you ever got there. And so I call this kind of a form of technical stakeholder engagement. You want to honor the existing analysts and scientists and database administrators that used to be there and use their prevailing method just as a check. Maybe it's linear regression, maybe it's doing counts and frequencies and pivot tables in an Excel spreadsheet, or it might be a tried and true method that is well documented in statistics. So for this example, we're going to use an ARIMA model, which is an auto-regressive integrated moving average. For those of you who are not familiar with ARIMA, ARIMA is basically a linear regression model that's correlating future values with past values, dealing with lags and moving averages. There are some nice functionality built. This is I shouldn't say this in a JupyterCon conference, but in R, God forbid. So there are some nice AutoARIMA packages in R, and then also you can use them in Python. Now, in order to build this model, we have to define a couple of parameters first. P for the number of our outer regressive factors, D for whether we want to difference it, meaning we want to get this time series data and remove it of seasonality and trend, and Q, the number of lagged forecast errors. So as a part of our exploratory analysis, I'll perform a Dickey-Fuller test, and that will tell me if forecasting only for pertussis, we've got a stationary data set. It tells me it's stationary, so I'm not going to log, transform, or difference it. We also have our plots here for autocorrelation and partial autocorrelation. And that tells me right here that I've got about 2 autoregressive terms, maybe all the way out to 5. It's outside of my 95% confidence interval, so we'll just go ahead and choose 5. And so now we've got our parameters, an ARIMA using the stats models package of 5, 0, and 1. So here I have the general ARIMA forecasting equation, and this provides another transparency value add. Why is it important to document formulas in a notebook? Well, there is always a classical fight that I have seen even in Booz Allen between mathematicians and data scientists. And a lot of mathematicians think that data scientists are this mystical thing that just came about and was cool and hot and hip. And so it's important to be able to talk about the statistics and the mathematics for how you're building these models. Why it's important to the government is this. In the government, I was talking about that talent gap. There are a lot of mathematicians in government. Have you ever been to NASA? Everyone's a mathematician. Or NSA? Everyone's a mathematician. So by being able to use something like, for example, LaTeX, which is an inherent part of a Jupyter Notebook. You can use MathJax, which is the library, I guess, the wrapper. You can use LaTeX, and you can write out all of your equations. That breaks things down and kind of encourages this communication between an organization that may have a lot of scientists, but not a lot of programmers. So we're going to go ahead and build our ARIMA model with that 5, 0, 1 parameters. The first 417 time steps we're going to train. The last 417 we're going to test. And we get a total mean absolute error of 6.63. Now, granted, this is only univariate. It's only for our pertussis time series forecasting. Could we explore a way to use an LSTM to build a multivariate forecasting? And how would that differ from this mean absolute error? So we're going to begin that voyage right now. But before I finish this, it's important to also exhaust every possibility for your ARIMA model. When you're building that baseline model, don't just ditch it because your first model had a low accuracy. Keep going at it. Try the best that you can as you would have the attention on your machine learning model to make this non-machine learning model as good as possible. So as I was saying about R, they've got an R AutoARIMA library, and there's a great package called Pyramid, which is essentially R's AutoARIMA library within Python. And so right here, we're basically going to grid search the entire space of these PDQ parameters to find the best AIC, which is essentially a measure of the goodness of fit. And so what we found here is that our AIC tells us that actually instead of 501, 201 was the best that we could do with our time series of pertussis data. All right, so we've gone ahead, we've investigated our baseline model, and we're going to start with our data processing. Here is the next value add takeaway. This is where you can really, really mess up. Our previous speaker talked about how 80 to 90% of building a model is dealing with the data. I myself have been guilty many times of doing the wrong imputation, taking the wrong amount of data. In neural networks, you're constantly dealing with NumPy, so you're reshaping things in multiple dimensions. You can screw up immensely in this step. So a part of the Jupyter Notebook value add for the government is to start chronicling what you're doing to the data. I guarantee you that if you step into any organization that you've not worked with before, they will know one thing better than you will ever know, which is the data. They will know their data better than you will know in the next year, 2 years, what have you. So as another part of that technical stakeholder engagement, honor their understanding of the data and be transparent in how you treat it. All right, so this metamorphosis in the data processing, let's first start with how we are going to standardize this data. Again, I'm using Lake Tech. I'm laying that out. Zero mean and unit variance for all of our 444 time steps. We want to talk about, in this particular step, if we're normalizing it, such are we going to scale it from 0 to 1? Sometimes these things do have an impact. Now I've gotten that CSV file of that 544 time steps for 6 different features: pertussis, influenza, salmonella, which are weekly case counts, by the way, precipitation, low temperature, and high temperature, and I've put them into a 2-dimensional matrix here. So our first 5 values have our 5 independent variables that we're going to use as our multivariate forecast. And then we have our target value, which is all of our normalized pertussis forecast targets. All right, now we're going to transform this data. And so this model is only good for a 1-week forward forecast. For the simplicity of the notebook, I thought that would be the most helpful here. So all we're doing is we're shifting our pertussis cases for the next week. And so now we're left with a new matrix of 543 by 6. All right, we're starting to talk about matrices, so let's get into this reshaping the data, the train test split. Here's your transparency value add. When you're dealing with deep learning, you are constantly dealing with reshaping data. From a business perspective, especially in an organization new to machine learning, they're probably going to give you a CSV. It might be highly dimensional. Have like 1,000 fields or 1,000 different columns, but they're used to working with just a tabular set of data. What the government organizations are interested in is they don't want just a result and walk away. They want to understand, again, what did you do to their data, because they want to be able to train their workforce too. This is, at least for me, the part when I began learning about neural networks, the most mind-boggling. I have notebooks and notebooks and moleskins of just drawings and whiteboards of how we assemble this data. This is from an excerpt from medium.com from Hacker Noon, and all it's telling you are different ways for you to think about the shape of data. We've got a 1D tensor or vector. It's just a whole vector of data. That's one. You can think of it in rows and columns, 1 column long. We have a 2D tensor, which is tabular data. Let's think of this in terms of rows and columns. Now we're getting that 2D tensor, and then we are adding additional features. Now I've got a cube. Cubes can be stacked, 4D, 5D. So when we deal with 4D and 5D, we're dealing with computer vision models that deal with images and full motion video. For the purposes of our time series forecast for an RNN, we're just going to deal with a 3-dimensional space. Again, what I've done here, which I'm a big fan of doing, is drawing. I draw a lot of pictures. I find that if I can't draw a diagram and tell you how I reshape the data or what the model architecture is, I actually don't know what I'm doing. And so this is also for the data scientists in the room who are working with other data scientists. I have a recommendation. Ask your data scientist, all right, you want to build this model, this convolutional neural network. Can you draw the architecture for the convolutional layers, the pooling features, the dropout? Can you draw that all for me? Because now we're talking the same type of understanding. So this is one first set of drawings, and you're going to see a lot of drawings in a minute. What's saying here is that I've got a training set of data, a validation set of data, and a test set of data. My training set, for the simplicity of this model, is 1 by 181 by 5. It means one very, very long sample of 181 time steps for influenza, salmonella, precipitation, low and high temperature. One long, long sample. First 3.5 years. My validation set is the next 3.5 years, and then my test set is the next 3.5 years. And what we have here are essentially 181 time steps in this vector. I've done this for each one of the 3 sets as I've just narrated to you here, our training set, our validation, and our test. So this is a very simple example that we're going to be walking through. All right, we are finally ready to build the model. So let's do this. All right, the transparency value add. Neural networks are hard to understand. I'm sure that there's a lot of people here who have done some deep learning. Maybe it's very easy to understand, but for me, it's hard to understand. You have to make a leap from understanding the fundamentals of machine learning and then apply it into a different type of mindset with neural networks. So as I mentioned earlier, by drawing out the architecture of this model, it not only helps the government understand what type of prototype you're trying to build, but it also tests your knowledge and understanding as well. So let's go over this at a very high level. On the equal sign, you'll see that there's a diagram to the left of it, and then you'll see a diagram to the right of it. This is a classic depiction of how one would talk about a recurrent neural network. On the right-hand side, you've got all of your X inputs, right? That's the 181 long time step for our training set. That goes into one hidden layer. We have one layer of LSTM units. You might call a unit a neuron. Some of you might have heard that term. One hidden layer, and my model is going to show you 128 neurons or LSTM units, and then we're outputting our target, which is our pertussis forecast. On the left side of our equation is this model, what we call unrolled. And what this is telling you is that at each one of the 181 time steps, we're going to feed it into our layer of all the LSTM units, and we're going to say, hey, because I built this in Keras, PyTorch is also a great framework. In our Keras model, I'm going to say, hey, Keras, give me a prediction at every single time step. That's why there's a wrapper that says time distributed. That's just an artifact of programming these LSTMs at every single time sequence in Keras. This is what some of you may have seen as a many-to-many sequence. You can also do a many-to-many sequence in other use cases like machine language translation, going from English to French. Here's another transparency value add. Now, as you can tell, we're ratcheting up a number of diagrams and opportunities for explanation. Every single neural network has all sorts of complexities. When you start researching the literature, you'll find that one researcher has made a better way of doing a bunch of convolutional layers or fully connected layers to a previous researcher's convolutional network, et cetera, et cetera. So there's a lot of research about different architectures. What's important and why I'm showing you this is because this is where a lot of government organizations get kind of stuck. They understood how you transformed their data. They understood kind of what you're going to be doing with the model, what is happening inside the model. And this is where the whole notion of a model being black box comes into play. So I'm not going to go over this in great depth. This is my own picture of my own rendering of Chris Ola's blog. So for anyone who is interested in learning about RNNs, you have to check out Chris Ola. But this is my own type of picture. And all I'm telling you here is that an LSTM is a special type of recurrent neural network. There are many regulatory mathematical operations that allow information to be inputted, written to, saved, and outputted in a regulated format using multiple different types of essentially linear algebra. This is what prevents this type of network from having a problem called vanishing or exploding gradient, or basically this is a type of model that will help it remember past historical sequences of data. All right, we're going to go ahead and define our loss metric here. This is the mean absolute error. And again, as I was saying, LaTeX is an awesome tool. Let's go ahead and use LaTeX and write out our formula. It's also important here that if there is a statistician or a mathematician on your team, consult them. Do not leave them out of the fold. There are many types of metrics that you could use. We could have used a mean squared error, probably not R squared, but we used a mean absolute error. Look at the other types of research and publications and what they're using. This is very important because this is going to define our loss and how well our model performs. Here we go. We're going to build our model. And what I showed you in my diagram was one hidden layer. I actually have two hidden layers. So we've got two hidden layers, 128 neurons in every single layer, one time distributed, a dense layer saying, give me one prediction at every single one of my 181 time steps. We've trained it for 200 epochs, and now we have our loss plot. Okay, here's a transparency value add when it comes to a loss plot. Now, as you'll see here, I've only plotted you the loss of the training data. That's because I only have one sample for the brevity of this exercise. So I can't really split 1 by anything else to give you a split of a train and validation set. However, giving you the overview of a training loss is not helpful. We really need to know the validation loss because that gives you the best estimate of how generalizable your model is going to be on unseen data. So in a future model, I'm going to show you in a couple of minutes, a second data processing approach. We'll be able to split 20%, 30% our training and validation data. And what makes it really helpful is that Keras has callback functions. Many libraries do, where you can be able to output your training and your loss curve in TensorBoard, for example. So here we have it on TensorBoard. These are about 6 different models that we ran. And now you can see that at the top is our training loss, but at the bottom is our validation loss. And you can see how all these different models stack up to each other when using the mean absolute error. Now this is helpful because being able to understand how well your model is performing, one peek into it is understanding your training and your validation loss plots. All right, let's keep moving forward. Let's check out how well this model did. Our mean absolute error for the validation set is 0.97. And then our mean absolute error for the prediction set is 1.52. Hey guys, this doesn't look very good. So our orange are all of our actual time series values, and then our blue is our prediction. Now, I could have sugar-coated it and shown you something great, and we would have like a super low loss and magic. But it's important to show people in a notebook, especially to a government, that there's a lot of room for iteration. Like I said, we've been working on this since around December, and I personally must have built like 100 different models. A lot of it is based on a lot of trial and error. Some of it is in art, reading a lot of literature, but not everything is peaches. So what this tells me here is that this model has been pretty good at predicting the overall trend, but it has a long, long way to go. All right, next step, get the model configurations. Why is this important? Well, you just heard me say that I probably worked on like 100 different models. I have been very guilty of repeating the same model again because I didn't write down on a piece of paper all the hyperparameters, I didn't write down how many epochs I ran, and I ended up running the same model again. Now, for one model like this, you can write it on a piece of paper. What was your activation function? What was your train test split? All these different knobs and levers that you've turned. But once you start building a lot of models, you need to be able to inventory them in a way that is organized and makes sense. I'm going to show you in the final master notebook how this really helps when you do multiple models. So here we're able to output all the parameters for each one of the 3 layers. So we've got our first layer, tells us our activation function was a tanh. We've got all these different configurations. Our second layer, we've got all these configurations. And our third layer, which is our dense, is our time distributed. For those of you in the audience who are looking at this and it looks like complete gibberish, the reason why this is important is because these are the hyperparameters. These are the knobs and the switches that you can turn to be able to make your model become more and more accurate. A lot of machine learning data scientists, they'll first start with a learning rate. They'll experiment with different optimization functions. And it becomes this big kind of Chinese menu for figuring out what are the best combinations to give me the best type of model. This is very important from a documentation perspective. If you forget your configurations, how can you reproduce this ever again? All right, now it's time to do something that I am personally starting to do a lot of, which is computing the gradients. So in a neural network, there is a backward pass. I'm not going to go into great detail about it, but when you're computing your loss function, you're going through a forward pass, like in linear regression, for example, but that's not the end of the story. You have to do a backward pass. And what that means is that we're doing a back propagation method that will compute the gradients. Gradient just means a derivative. It's a rate of change for multiple variables. But then after that, we optimize those gradients, and that makes the model learn. And what ends up happening is that all the weights across the entire network are adjusted a little bit up, a little bit down, so that we're minimizing the mean absolute error, that loss function at the very end. Now, there is a trick in computing gradients where you can compute the gradients of the inputs, of the output vector with respect to the inputs. All that is telling you is a form of sensitivity analysis. I want to be able to do something kind of like you might see in a random forest. Has anyone ever used a random forest model? And so in scikit-learn, they make it super easy. Feature importances. I can see all my features, which ones are more predictive. Business leaders love to see that. You can do derivations of it and permute and destroy an entire column, rerun a model again, do it hundreds of times, take the average, and now you can get that feature importance. How can we do something similarly to a recurrent neural network? This is one way of doing it. So what this is telling me is that the prediction, my pertussis forecast, is most sensitive to which one of my 5 independent variables. Is it influenza? Is it salmonella? Is it precipitation, low or high temperature? Now again, it's important, when you're doing something like this for a new organization, please use LaTeX. Please document your references and talk about what it is that you're doing. Just for the folks in the audience who don't do a lot of calculus, that a derivative is just the rate of change with regard to one variable, and a derivative is just a fancy way of saying it's a matrix of multiple values of partial derivatives. It's a derivative with respect to multiple values. We have multiple values, 5 independent variables. All right, this is the same depiction of the previous diagram where we unrolled it, but we've got our inputs. We've got 2 hidden layers of 128 units, and this is our output. We want to calculate the gradient of the outputs with respect to our inputs. This is similar to something that maybe you've seen before out in the literature. In this one example from another Medium blog post, he wants to know, for my text classification score, which one of my words are most sensitive to that score? And he found that Coke is the most sensitive. But he's using the same type of analysis, computing the gradients of the output with respect to the input. This is also similar to something you might see in computer vision, which is they use saliency maps. The idea being able to compute which one of the pixel features in this image is most sensitive to my prediction. So when we go ahead and we do this, we're going to get our gradient. These are all the partial derivatives for our training set. And we can just get the mean or the average of all the absolute values of the gradients for each one of our 5 features. And we'll see that only for this training set, salmonella seems to have the largest gradient. It is the prediction is the most sensitive to changes in salmonella than, let's say, compared to high temperature. And we plot this out, another value add for Jupyter Notebook. We're able to see only for our training set that we get a plot. And this shows a plot of how all the gradients, their absolute value of the gradients, have changed over time with respect to the predictions. And what we see here is that we see a blue curve and an orange curve, pretty much the largest gradients here. And that makes sense because our previous mean average showed us that the strength of the gradient, the magnitude of the gradient, the predictions are the most sensitive to salmonella and influenza. Now this provides more of an intuition. This is not an absolute science. If I added the entire 544 time steps instead of just my training step of 181, this would change. So this is something that is our attempt at being able to understand the inner workings of a black box, especially with neural networks. And I think it's very important for interpretability to begin this process. All right. Now, I showed you the model where we used 181 time steps, one single sequence. And we used time distributed. And we said, give me a prediction at every single time step. And we got a bad loss function. It was not a good prediction. This is another opportunity in a Jupyter Notebook to start exploring maybe a different type of approach. Instead of having one long sample of 181, can we show in this Jupyter Notebook how maybe we could have multiple samples but overlapping sequences? And this is kind of natural to a supervised machine learning approach. So here what we've done is we provided overlapping sequences. We now have building our model. We have our loss plot, so we've now seen that our training and our validation loss have converged quite well. And now we're able to output our score predictions. So for the test set, our score is 0.897. And then you'll be able to see here with this new data processing approach, it's a little bit closer to our predicted values. But we still have a very, very long way to go because we can still see a big difference here. Now, at the end of this notebook, we'll be able to use those configurations. Let me just expand this a little because it's a little bit hard to see. But remember when I was talking about the model configurations? We're now able to get kind of an overview of the different models that we built and then their mean absolute errors. And we can customize this output so we've got other configurations to show. But in our final master notebook, this is really helpful because as we build more and more models, just give it a little minute, we'll find that this is a good way to keep up with all of the models that we've built, and we've tracked that mean absolute error. We want to build the model that has the lowest loss function. And this reminds me a lot for anyone who's done work on Kaggle and just participated in Kaggle competitions, going up the leaderboard and building a leaderboard of your own of different models that you've built. One of the things I really want to do with our team is, as you can tell, a lot of this is just hard-coded just for me preparing this. But what I'd really like to do is build a toolkit in Jupyter that everyone can use, put it up on GitHub, that will have like a running leaderboard pandas output so that everyone who's building a notebook can do a running leaderboard and you can just summarize all of your models at the very end. At the baseline, I think that would be super helpful to have. All right, so let me just show you a couple of things. I've got a little more minutes here. This whole notebook is available here up on GitHub on my account. So it's Nudro, which is my last name spelled backwards, Ordun, and it's Jupyter Forecast. Here are all the dependencies that you will need. And then here's the data set. And then here's the notebook up here. So this is going to be something, if you have any questions about it, do not hesitate to give me a call, and I'll help you think through it. Also, I have this notebook, well, you could actually do this too, up on Google Collaboratory. So Google Collaboratory is something that at Booz we started doing a lot of, especially when it comes to tutorials and teaching each other. And the reason why is this. Maybe some of you have been asking, Catherine, you built a neural network. Where is the GPU? And so at Booz Allen, we have a partnership with NVIDIA. And a lot of our data scientists are like NVIDIA deep learning instructors. I'm one of them. And because of this partnership, we have our own NVIDIA cluster. We've got 3 different clusters. And so I always tunnel into an NVIDIA cluster. It's got 4 Titan cards. But for this model, when you download it off of GitHub, you don't need to run it on a GPU. It's only 544 time steps. It's only 6 different features. They're all numerical. I have a MacBook Pro. It's got 6 core CPUs. I just run it. It takes like less than a minute. When you're dealing with large processes, obviously you need a GPU. That's why a Google Collaboratory notebook is really cool. For 12 hours, you can run it on their GPU, which I think is equivalent to a P2X large in AWS, which is equivalent to like one like GeForce card, I think. Don't quote me on that. But when you run it in your Google Collaboratory, you can run this model, and it'll run really fast, or just as fast once it starts running here. Let's do this. Because Google Collaboratory, all your neural networks can be built on their GPU 12 hours free. So I would highly recommend that you get your notebook and you build it into Google Collaboratory. We use it a lot at Booz Allen for our tutorials, and I think that's really neat. So let me go ahead and close this out here, and I'm going to go back to our slides really quickly. So what I walked you through was the value proposition of why being transparent with machine learning model for the government is helpful. I hope that came out clear. I also walked you through, just by itself, showing you the one model code is ordinary. But if we show you all the different features for multiple models, that provides one step towards being transparent. I also walked you through the notebook, and now you have access to it on GitHub. I highly recommend that you run it in Google Collaboratory. I would recommend, as kind of a final call to action, is practice considering some of these transparency steps. It's everything that we talked about today. The baseline model, the data processing, building the model configurations, computing the gradient. Something I didn't show you because it's sometimes not really worth it, is the different weights. So you can actually output the weights for every single neuron, for every single gate of the LSTM. But for this talk, I think that would get too much in the weeds. That might be helpful, but computing the gradients is more helpful. And then also to summarize your models in the end. I recommend considering some of these recommendations. Your clients may not be in the government, but they may be organizations or stakeholders who are also starting to learn about machine learning. And I would emphasize, be easy on them. Try to make it as easy to swallow as possible, and hold their hands and guide them and educate them, because they are trying to use your models to do something very important for their organization. So with that, again, do not hesitate to email me. I'm more than happy to answer questions now or in the hallway. And you can also follow me on Twitter as well. Sometimes I repeat and retweet interesting machine learning articles. So thank you very much for your time, everyone. Yes, sir.
How important is, in addition to transparency, portability of, let's say, net, as well as repeatability in outside environments, say beyond Jupyter, like you mentioned, doing some analyses in R to ensure that there weren't biases introduced in the code stack floating point computation introduced in Jupyter, for example. So repeating it in Mathematica using an import format like Onyx or MXNet, like just as a comparison.
Yeah, I mean, I myself have read a lot of Stack Overflow and cross-validated posts about this very topic, where even, let's just forget Python to R, within stats models, sometimes I get an error. It's called maximum likelihood estimation convergence error. And I'm like, why am I getting this error? And sometimes it's because people have not updated the recent package of stats models. Sometimes they've changed documentation on the back end, so the actual ARIMA forecast or the Ceramax forecast is not working appropriately. So, I mean, that's one root cause about why it might be happening. Some of it comes down to inspecting the source code. So, yes, obviously it's important, because in our teams, not everyone is, I mean, I don't tell people, you have to do this in Python, or you got to do this in R. Whatever language they're familiar with and they can do good work is what they're going to use. But regardless, R has an advantage in that it's very statistical, as a lot of statistical models, mathematicians use it, epidemiologists use it, and sometimes it's not a one-to-one mapping. If you're going to build an ARIMA model in R, it's not the same output. It's like a little bit off from what you might see in stats models. So kind of the solution there is to look at the source code and maybe do this, which is the reason I put all those mathematical formulas in LaTeX is because although scikit-learn is incredibly well documented, although every single NLP package is built on the back of NLTK, if you are able to reproduce your model with your own mathematical formula, I would suggest that you try it. For those folks who are building neural networks, don't just immediately go into Keras. Try to follow tutorials that use NumPy and do it from bare bones from scratch. So I don't see like an immediate way to solve this writ large. I think it's a class-by-class problem that requires investigating the source code, but actually just having the guts to try to build it yourself mathematically, if that's something that's possible. Yeah. Yes, sir.
So I was late, so I don't know if you were mentioning this, but as a first pass, especially since we have a lot of time series analysis, like instead of looking for correlations in the time, did you look at any sort of causality analysis, like direct causality, to see if there was features that were specifically not just correlated with the output, but causal?
Well, I mean, I think that I'm going to answer this in this way, which is one of the features that we used was salmonella. Now, for a lot of the folks in public health, you might think, there is no relationship really between salmonella and pertussis. Salmonella is bacterial, pertussis is also bacterial, but influenza is viral. So a part of this causal analysis, I think, first goes to consulting with a subject matter expert and determining whether the feature that you're going to be using in your analysis has any logical relevance at all. That's number one. Because I could get diapers and beer, and I could maybe correlate that with pertussis, and I'll say, oh, well, diapers and pertussis have something in common. For the causal analysis, no, we didn't look at that for this time series. We were really focusing on being able to do a prediction. However, I think that that would be a next step. I've got a couple of ideas about maybe how that would work, but I think this is such a hard space in terms of disease. I mean, it's a very hard space in terms of disease. It's hard to say if the influenza cases are causing pertussis. We can say there are correlations, but causation in itself is kind of hard to define. But I'm more than happy to have some ideas from you later on. Thank you. All right, well, thank you very much. And if you have any questions, let me know.